Hello and a warm welcome to my little explainer on input-output management and operating systems. My name is Sanjay Sundaresan and my registration number is 19BPS0013. So let's get started on what is an exciting little component in the world of computing. Input-output is something that may have generated some curiosity in the mind of anyone who ever comes across a computer. Questions like how exactly does the magic happen inside the computer? Those are the kind of questions that I look to answer in the next few minutes. Input and output may seem fairly simple to the user, but that simplicity takes a lot of work behind the scenes to achieve. Whatever the user sees is quite orderly, but that's made possible only because the operating system does an excellent job of hiding all the chaos beneath it all. So in due course, I'll be taking you through how exactly the operating system manages to achieve this. Before we start, let's certify our basics. Input and output can be viewed in terms of stimuli, wherein input is the stimulus generated by the user towards the system, and output is the processed response of the system to the input. The processor and memory will be involved in the processing stage, as it's clear from the image. The necessity for I/O management can be understood by what is called a domino effect between the frequency of occurrence, the rapidity of the operation, and the interrelation between them. Almost anything you can think of in day-to-day applications will involve some component of input-output. So at the most basic level, the main functionality of a computer functionalities of computer are input-output and processing. So there are some instances where there are in fact multiple instances where input-output supersedes computing functionalities. Watching this video, browsing the web, reading or writing a document on your computer, listening to music, attending online meetings, the list is endless. So almost 80% of the activities performed by the average user on a computer involve little to no focus on computation. So that's why it's important to achieve, important to appreciate the vitality of timing and coordinating input-output operations, most of which occur rapidly in real time, with each operation having its own effect on the others. This brings us to the approach that we'll use to understand what happens behind the scenes of this rather coordinated little play. A bottom-up approach is the simplest way to understand I/O management, as we start from the hardware to understand what an input-output device does and work our way up to the top application level via the kernel of the OS. We explore every component discussed in the approach as we follow a bottom-up paradigm. We shall discuss the hardware first before we delve deep into the supporting hardware and the software, and that is the OS routines that ensure control, coordination, and communication among the devices themselves and also with the user. So the first basic question is, how is input-output managed? The answer, very simple, it lies in the question itself, the operating system, that's the manager. Just imagine you're Tony Stark for a second. Jarvis is your little AI assistant who makes life easier for you by managing all your gizmos, coordinating, controlling them, make sure they communicate smoothly with each other. This is exactly what an operating system does in terms of input-output management. But managing every single device is not feasible because they come in various shapes and sizes and various complexities and functionalities, as I'll be discussing later. So the operating system has some workarounds for these complexities. We'll be looking at that later. It's a very, very interesting concept of what exactly the operating system does. So data received from the user through an input-output device is stored in the memory, processed by the processor, and the information is given to the user once again through the input-output devices. So it's clear that various devices involved in the story will work at different speeds. The whole process is somewhat similar to a story or a play in a theater. This is why it's important for the operating system to write the storyline and punctuate it to perfection, and that perfection is achieved by a collection of input-output oriented routines in the kernel called the I/O subsystem. We'll take a look at this in detail a little later. A little animation for you to understand what I'm talking about in terms of the story. You see the data input, the memory, a rather funny processor here, and ultimately the monitor, which is in different modes at different points of time, which is exactly what happens in a real-time scenario. So this brings us to the categorization of input-output devices. This is the first aspect of the hardware that we'll be looking at. So there are various verticals for categorization, and one such vertical is the degree of user interaction. We have three broad categories when it comes to this. One is the interface device, which is involved directly in the I/O process, such as the monitor, the keyboard, the mouse and the speakers, etc. We have the transmission devices, which essentially transmit the data gathered. They're used mainly in networking. Then the third category is the storage device, which will store the data gathered by the interface device. The best example for this would be a disk. This brings us to the enablers. The enabling hardware, as the name suggests, it helps achieve some generalization between input-output devices. So these enablers work directly with the operating system, eliminating the need for direct interaction between the kernel and the device hardware itself. So there are three main enablers here: the ports, the buses, and the controllers. A port is a preliminary communication point between the input-output device and the machine. When I say machine, I mean the rest of the hardware. And bus is the interconnection system, sort of the backbone. We can call the bus a backbone of the system because it's going to connect various hardware devices with each other to facilitate the transfer of data. Not only the hardware devices, it's also going to connect the main hardware device, which is the processor, with the other devices which the processor will be working with or manipulating. So the bus is by far the most important component here after the controller itself. Coming to controllers, so the controller is a hardware device that is able to manipulate a port, a bus, or an input-output device. Not only input-output device, hardware devices in general tend to have controllers. So a controller can range from a small part of a single chip to being as big as requiring a separate circuit board. So all these bigger circuit board controllers are used to control complex buses, which I'll be talking about in due course. So since buses form the vital interconnection functionality without which the hardware devices would not be able to communicate between themselves, it's important to understand their role. There are two types of buses: asynchronous buses and synchronous buses mainly. Asynchronous buses have handshaking protocols, and synchronous buses perform specific operations at specific clock cycles. So buses will have arbitration mechanisms. Arbitration is basically control granting, and bus protocols to govern the behavior of the devices and ensure smooth communication. Usually a master-slave approach is used where the master initiates the dialogue. Most commonly the master is going to be the processor or the direct memory access controller. Let's say a bus is going to be one of the most important aspects that we will be looking at when it comes to input-output management. Even though it's not software, it is an extremely important part of managing the various input and output operations that have already been established before. We've seen that they occur rapidly. So it's important to carry the data between these devices as quickly as possible with minimizing with minimal error, basically. So this is a typical bus. You can see that the device controllers are interfaced with the bus. An expansion bus is needed to bridge the speed gap between low-speed devices and high-speed devices because the speed of the bus is governed by the speed of the slowest device attached to the bus, which is why we cannot have devices of varying speeds attached to the same bus. PCIe essentially stands for Peripheral Component Interconnection Express. This is the most common bus used in modern systems, and we also have the expansion bus, which as I mentioned before, is used to bridge the speed gap. So you see this little controller there called the SAS controller. SAS is nothing but serial attached SCSI. SCSI stands for Small Computer System Interface. These are what we call host controllers. They're basically device connectors used to interface with the bus. So next question that comes to mind is, how exactly does the processor communicate with these devices? It's the most simple aspect of input-output management, yet there is so much intricacy involved here. There are a lot of complex processes happening. The abstraction that the operating system provides does an excellent job of hiding all this from the user, which is why we're not able to actually dissect from the user level, and this is why we have to build up from the hardware level itself. So there are two methods of communication with the processor. One is the special IO instructions, and the second is the memory mapped IO. Special IO instructions basically trigger the transfer of a byte or a word on a bus line, whenever the instruction is encountered, the device controllers tend to have registers, data registers, status registers, and control registers. So as the name suggests, the control registers will be used to control the devices. Status registers will be used to indicate the status of the device, whether it's busy executing or it's free to receive data or send data. The data registers will store the input or the output data. The whole concept is quite simple, but when we take a look at memory mapped I/O, this is what's preferred in modern systems, because there is no demarcation between the input-output port addresses and the regular memory addresses, which is why the simplicity increases even more in memory mapped I/O. The device control registers will have addresses that will be part of the address space of the processor, which means the processor does not see them as separate entities. The input-output ports and the regular memory, the addresses will not be seen as separate entities. The processor looks at them as one single block, which is why the CPU will be able to execute input-output requests using standard data transfer instructions to read and write the device control registers. Continuing on the communication with the processor part, there are two ways for the processor to realize that the input-output operation has been performed by the device: polling and interrupt-driven input-output. So polling is used in non-memory mapped systems which have the periodic checking paradigm. Periodic checking essentially here means the status register of the input-output device will be checked periodically by the processor to indicate whether it's busy or it's free to receive or send data. Polling, it's an old concept. It's not used in modern systems. Modern systems instead tend to use interrupt-driven input-output, wherein the interrupt control hardware handles interrupt requests from input-output devices through an interrupt request line. This is interrupt control hardware essentially here refers to the interrupt controller, which is a hardware device used to manage all the interrupts generated by the input-output devices. There are software interrupts as well. And those are triggered by system calls, which you'll be familiar with if you're an operating systems learner. So the interrupt control hardware, it's going to receive requests through the interrupt request line, and the kernel interrupt service routines work with the interrupt controller. So further, there are two types of interrupts: polled interrupts and vector interrupts. Polled interrupts, the interrupt controller knows that there's an interrupt but does not know the device's origin, so it's going to poll every device to determine the identity of the device. It does not know which device is trying to interrupt the processor. In vector interrupts, the device identifies itself by referencing the interrupt vector table. The interrupt vector table is basically contains interrupt numbers mapped to the corresponding interrupt service routines via the use of pointers. So it's going to have a pointer to the interrupt service routine for a particular interrupt number, and the processor will automatically know which interrupt service routine to execute as part of the kernel. A little animation of what I was talking about here. You can see a magnifying glass in the first still and a man trying to interrupt the other man in the second still. Magnifying glass, that signifies the searching. There are multiple input-output devices, and it's searching for which device exactly generated the interrupt. And the second device, the process is busy doing its own thing, and the input-output device, as soon as it completes the operation, it's going to tell the processor that, see, I'm trying to tell you that I have completed the input-output operation. This brings us to the next part. As we move to the software part of I/O management, it's imperative to understand the characteristics of input-output devices and the various verticals used to classify them. You may recall that we explored one such vertical earlier in the form of user interaction. Let's take a look at this categorization in terms of the other verticals now. We have character stream or block devices. Character stream device transfers bytes one by one, whereas a block device transfers a block of bytes as a unit. Next, there are sequential or random access devices, wherein a sequential device transfers data in a fixed order determined by the device, whereas the user of a random access device can instruct the device to seek any of the available data locations. We also have synchronous or asynchronous devices, wherein a synchronous device performs data transfers with predictable response times in coordination with the other aspects of the system. An asynchronous device exhibits irregular or unpredictable response times not coordinated with the other computer events. So The other classification can be in terms of shareable or dedicated devices. A shareable device can be used concurrently by several processes or threads. A dedicated device cannot. Speed of operation is yet another important aspect that dictates I/O management. Device speeds can range from a few bytes per second to a few gigabytes per second. An excellent example for this would be the speed difference between a monitor and a printer, because a printer, since it has to perform so many other operations, it's not able to concentrate on the communication between the disk and the printer itself, which is why it cannot physically handle the amount of data that the file that's capable of being sent, which is why the concept of buses comes into play. The direction of input-output operation provides another means of classification. This is probably the most well-known classification, because we have read-write devices, we have read-only devices, we have read-only memory, we have programmable ROMs, we have electronically programmable ROMs. So some of these devices, they perform both input and output, but the others support only one data transfer direction. Some will allow data to be modified after write, but others can only be written once and then they'll be read-only thereafter. So before we jump into the software, make sure that you understand this demarcation very, very clearly. You'll be seeing why I'm stressing on the importance of this characterization, this categorization, because the software paradigm that we follow, that's going to depend completely on how this categorization takes place. After looking at the devices themselves, it's time to jump into the software part of the input-output management, and this is the part where the role of the OS becomes more clearly marked. So make sure you have the categorization of devices in mind as we proceed forward. Like any other complex software engineering problem, the approach here is going to involve abstraction, encapsulation, and software layering. So specifically, we can abstract away the detailed differences in input-output devices by specifying a few general kinds of device specifications. So each general kind is accessed through a standardized set of functions. That is an interface provided in the form of a device driver layer. Device drivers are special software programs that map a specific input-output device to the category it belongs to, so that the kernel I/O subsystem is able to see only the various categories of devices that it can manage through the interface, and not the actual unique devices themselves. So the device driver layer, we can say it's analogous to the system call layer, because it forms the core of the abstraction that is so essential for the operating system to manage input-output devices. So it's extremely important to understand that the hardware-software connect provided by the device drivers, they work directly with the device controllers. There are block device interfaces, there are character stream interfaces, there are socket interfaces, and so on, for the various characteristics of the input-output devices that we just explored before in the device driver layer. We've seen how the device controllers and the device driver work together with the input-output subsystem to control the input-output devices. I'll talk about the kernel I/O subsystem, that is the kernel input-output subsystem, in a short while. But before that, the key point here is that abstraction occurs not only at the user level, but also between the I/O subsystem and the driver. As we come down from the application level to the hardware level, the abstraction, the costs, the efficiency, and the generation time will increase. This obviously means it's done to guarantee higher flexibility at the application level. You can see the new algorithm, there's an application code that maps the kernel code. Kernel code is going to trigger the corresponding device driver routine. The device driver will work with the device controller, which is obviously the hardware part, and the device controller is finally going to manipulate the device itself. You can see from the image very clearly that as we go up from the bottom, there's going to be more flexibility, and we all know that flexibility is directly related to the abstraction, which is why abstraction forms such an important part of input-output management right from the outset. So here's a little abstraction meme for you to understand the role of the driver better. But don't be fooled by the animosity here, because all these three, the device controller, and the device driver, they're very much capable of working together. This is just something that will help you understand the abstraction. I hope you'll appreciate that. This is simply a more serious pictorial representation of how the abstraction is achieved. So you can observe a small gap between the device driver and the controller. That gap signifies the hardware-software jump during the execution of input-output operations. So as you can see, every device has its own controller and driver, but the input-output subsystem, it does not necessarily see every single device as a unique entity. This is also why you can simply start using a pen drive or a Bluetooth speaker without having to write specific kernel routines to control them. The device driver gets integrated automatically when the device is plugged in, because the operating system knows which category the device belongs to in advance. As you can see in the picture attached to the right, there's a device driver software that's being installed as soon as the device gets plugged in. Now, once again, here SAS stands for Small Computer System Interface. SAS stands for Serial Attached SCSI. That SCSI stands for Small Computer System Interface, and SATA stands for Serial Advanced Technology Attachment, which is not shown in the picture, but SATA is an alternative for SAS in bigger systems. So all these host controller interfaces, they play their own part in I/O management. The whole thing, I think the whole thing can be picturized as a perfect circus, because there is so much activity being involved. It might seem silly from the outside, but when you look at a circus, you see the logistics involved, you see the coordination between the various artists and even the animals. You'll observe that the input-output subsystem, the input-output management is perfectly relatable to a circus. So this leads to the details of the execution of an input-output operation. We've looked at how the operation occurs from an operating system perspective, but let's just shift our focus to the user perspective, because a very common scenario is that a user program needs an input-output operation to be performed. We go back to our good old system calls for this purpose. So system call interface is going to invoke the corresponding system call according to the API parameters. API here obviously refers to application programming interface. So let's suppose it's the read operation in this case. The context switching is done and the read operation is performed in kernel mode using the corresponding device driver and controller before returning control to the calling thread. It's very clear from the picture. But what will happen if a hard real-time application cannot wait to regain control? If the user application insists that the control must come back to the user mode as soon as possible, what's going to happen in this scenario? How the operation is going to be performed? We'll look at it right now. That's my segue into blocking and non-blocking I/O. So this need for urgency will bring us to the type of input-output operations that can occur with respect to the wait time spent to regain control. In blocking input-output, the control is returned only after the operation is performed. So this is called synchronous programming. And in non-blocking input-output, it's used by time-critical applications such as networking. The system call does not halt the execution of the thread for an extended time. Instead, it returns quickly with a return value that indicates how many bytes were transferred. So this is called asynchronous programming. So to summarize, there are two ways for the application to regain control quickly. One way is for an application writer to overlap execution with input-output. He or she can do that using a multi-threaded application, wherein some threads can perform blocking system calls while others will continue executing. Or they can use non-blocking I/O system calls, wherein non-blocking I/O system calls they can be used if the OS provides it. The logical question here is that how exactly does the application know that the requested input-output process has been completed in case of a non-blocking system call? So this is done through an internal variable in the application itself that changes value when the operation is complete, or through the triggering of a signal or a callback routine. A callback routine is essentially executed outside the sequence of instructions that will appear in the application itself. This is a pictorial representation of blocking and non-blocking system calls. You can see that you can follow the black arrow marks in the picture. The asynchronous system call the control is going to return to the process almost immediately with minimal time delay, while the synchronous system call is going to give control to the process only after the completion of the input output. You can see that the arrow mark, it is going to come back to the user land only when the operation is complete inside the kernel mode. This brings us to the kernel IO subsystem, the last aspect of the software part of input-output management. So the kernel IO subsystem is a collection of OS routines that provide various IO-related services to the user by talking to the hardware via the device drivers in the controllers. Some of the services at the glance are namespace management, which is needed to distinguish between devices and files. Files and IO devices may need to be accessed by multiple applications at various points of time. So the IO subsystem has routines that can be triggered by the interrupts or system calls. In memory mapped IO, file space allocation is done by the IO subsystem. This brings us to the other features. We'll be taking a look at some of the most important features such as IO scheduling, error handling, power management, spooling in detail. The first important feature is IO scheduling and buffering. Scheduling is one of the most important services provided by the IO subsystem. It's analogous to process scheduling. So let's imagine this scenario for a second. Imagine you're in the market, and your mother asks you to get an item, say item 1, which is at the end of the aisle, and your dad asks you for an item, say item 3, which is in the middle of the aisle, and your sibling is going to ask you for an item, say item 2, which is at the beginning of the aisle. You can minimize the time spent at the market by procuring item 2, item 3, and item 1 as you walk along the aisle. So the same thing applies to a disk arm in IO scheduling. The disk arm, you can minimize the distance moved by the arm of the disk. When it comes to an input-output operation, that's a little analogy. So buffering is another important aspect of input-output management because it helps account for the differences in hardware capabilities of the devices. Buffering is used in mainly 3 scenarios. The first scenario is when the drive write speed may be considerably higher than the rate at which data is being received. So a buffer may be used to store the data and write it in bulk to the disk. The second scenario is when different data transfer sizes occur. This happens mainly in networking because the data, as you know, in networking is broken down into fragments. So in this case, there are devices which will work with different sizes of data, which is why buffers will be used for reassembly. This brings us to the third scenario, which is, in my opinion, the most interesting one, copy semantics. So with copy semantics, essentially it ensures that the version of the data written to the disk is guaranteed to be the version at the time of the application system call. So independent of any subsequent changes in the application itself, basically even if the application data changes, the integrity of the write operation will be preserved because the presence of the buffer that holds the data that was to be written originally, it will ensure that the write operation takes place from the kernel buffer rather than the application itself. So the data that was intended to be written still gets written in spite of change in the application level. So this was the IL scenario, the scheduling. Let's move on to spooling and device reservation. So it's already been established that multiple input-output operations may occur at the same time. So spooling is one such service provided by the kernel that enables multiple outputs. Spooling is basically a combination of buffering and queuing. Spool stands for simultaneous peripheral operations online. Spool buffer, it's going to store data from various processes or jobs so that the processor or the output device may fetch them at their own convenience instead of coordinating with the devices directly. Since there's no interaction of input-output devices with the CPU does not need to wait for the IO operation to take place. So the input-output operations comparative to the CPU operations, they take a large amount of time, but spooling is something that manages to reduce the time consumption considerably. When you look at the overall process, the processing and input output involved in an application. So it's important to know that there's a major difference between spooling and buffering. In spooling, the input output of one job can be handled along with some operations of another job, but in buffering, only one job can be handled at a time. So this automatically is going to indicate that spooling is more efficient than buffering. In fact, buffering is just one aspect of spooling. A little printer scenario for you to understand. You can see that the printer continuously receiving some documents to print. That will obviously, if those documents come from a spool queue, it makes the job of the printer so much easier because it does not need to take care of the timing, the coordination between every single I/O device. And the document that needs to be printed. It does not need to coordinate with the disk so that it needs to wait for the I/O device to put it on the disk through the bus and then onto the printer. That is why spooling is so important. So like any other software, error handling is an important aspect of the kernel I/O subsystem as well. The kernel must ensure that the hardware failure or overloading does not cause the system to fail completely. This is not something that will be pleasant to watch at all. Although this is a very old fail message on Windows XP, I think, but the gist remains the same nonetheless. So the error handling is done by return values of system calls and the mechanism to retry the failed operations. Some of the important hardware devices such as host interface controllers that we talked about before, controllers like SCSI, Sas controllers, they have advanced error reporting mechanisms with up to 3 levels of detail to help pinpoint exactly where the lapse occurred. So input-output protection will ensure that an inadvertent or malicious action by user does not damage the system directly. It so happens that we might, in memory mapped I/O, the user will be able to use specific port-oriented commands to access the input-output devices directly. But to avoid this, input-output instructions are categorized as privileged, and the user can only access them by requesting the kernel I/O subsystem, which in turn can be trusted to handle the whole operation because obviously the kernel I/O subsystem is part of the operating system. This is also why the kernel is going to reside in a protected space. Error handling is, let's just say error handling is one of the most underrated aspects of an operating system, not just in I/O management, but in every other aspect as well, because in input-output devices, because of the hardware complexities, it becomes that much more important to ensure that the system failure does not occur. So this brings us to power management. When we think of kernel input-output services, power management does not exactly come to mind. It does not exactly strike, but it remains one of the most important parameters in mobile and cloud computing. So I've included mobile and cloud computing here because it's the future. Every computer is trying to become more compact as we move forward, and cloud computing, as you know, is extremely powerful. So when we work with mobile and cloud computing, power management becomes that much more important. So the kernel I/O subsystem will be able to dictate how much time the CPU spends executing the device driver code, the amount of time the input-output hardware is active, which in turn impacts the power consumption. Every system would like to have unlimited power, because who wouldn't like to not recharge their batteries periodically? But unfortunately, mobile and cloud computing devices, they only have a limited amount of power to work with. You don't have the luxury of keeping them plugged in at all times, which sort of defeats the purpose of them being mobile. So that is why they have this advanced configuration and power interface, ACPI, which is an industry standard for modern computers that provides routines for device state discovery management, device error management, power management being the most important one. So for example, when the kernel needs to lower the activity of a device, it's going to call the corresponding ACPI routine, and these routines will talk to the device via the drivers and the controllers. The ACPI routines will be embedded in the kernel I/O subsystem, which means it can be treated as a modular kernel routine. This just shows you that the modularity, it increases drastically when we move towards mobile and cloud computing. It's the future. So finally, we are able to put together everything, all the hardware and software processes involved here when an I/O request is done. let's just say a process issues a blocking read system call to a file descriptor of a file that has been opened previously. So the request is going to travel through the kernel mode to the kernel mode to the kernel IO subsystem, and then onto the device driver. It just travels on from the top to the bottom, the interrupt handler, and ultimately the device controller. Essentially, the hardware software jump, as I mentioned before, happens from the device driver to the interrupt handler. So the device controller will then ultimately execute the command before it travels back up to the user space where the program regains control. All this is a summary of what we just discussed over the past 20 minutes or so. The last part, to conclude, it's important to appreciate the impact that input-output has on the CPU, the system buses, the memory, and almost every other aspect of the system you can think of. Some high-end devices, they have CPUs dedicated to input-output. These will be called IO channels. This ensures that the CPU will remain free for data processing. So, what we hope to understand from the video is that effective input-output management has a huge impact on the system, and it can make or break how the system is viewed by the user. So we can employ a lot of principles to improve the efficiency of the input-output management. We can reduce the number of context switches. We work on reducing the number of times the data must be copied. We reduce the frequency of the interrupts by using large transfer of data. We increase the concurrency using direct memory access controllers so that the CPU overhead is minimal. We move the processing primitives into the hardware to allow their operation in device controllers to be concurrent with the CPU and bus operation. This is sort of the asynchronous programming approach that we discussed. The balance between the CPU, the memory subsystem, the buses, and the input-output performance is critical, because an overload in any area will cause idleness in the others. So I leave you with this animation in Windows XP of a cat running across one of the most famous desktops. Thank you very much for your patient listening, and I hope you had fun exploring this seemingly innocuous little concept that plays such an important role in our daily life.